Hello everyone. We are going to be doing standard normal distributions. So the first thing is, what is a standard normal random variable? A standard normal random variable is first of all denoted by the capital letter Z, has a normal distribution with mean 0 and standard deviation 1. So similar in the fashion when we said X has a normal distribution with mean mu and standard deviation sigma. So a standard normal distribution Z, or we can call it a standard normal random variable, has a normal distribution with mean 0 and standard deviation 1. Similar to what your normal distribution is, it has a density function which is given by this equation. That's good to see, but what our main focus is, how can we write a graph of this density function of a standard normal distribution? It's the same as the normal distribution. It is a bell-shaped curve, but at the same time, the mu now here is 0. Okay, and you go, if you go to the left, right-hand side, you go in increments of 1 because the standard deviation is 1. So this means 1 standard deviations, 2 standard deviations, 3 standard deviations to the right of the mean mu, which is 0. And as we go towards the left-hand side, we have -1, that means 1 standard deviation to the left. -2 means 2 standard deviation to the left. And -3 is 3 standard deviations to the left of the mean 0. Now, how would we use our calculators? The formula is, if Z has a normal distribution with mean 0 and standard deviation 1, if it is looking at the probabilities between the lower and the upper end, A and B respectively, we write normal CDF, the lower end A and the upper end B, and by default it is 0 and 1. So that's why whenever you can simply write normal CDF and you write A and B, by default your calculator will assume that you're in a standard normal mode. Okay, so let's see the relationship of the standard normal distribution with the normal distribution. Okay, so when we say that X has a normal distribution, that means we are talking of a normal distribution with mean mu and standard deviation sigma. Then we say if we have this variable, this capital Z, which is basically the capital X minus the mean mu and sigma, then this Z will have a new distribution, but the new distribution is again a normal distribution. It will have mean 0 and standard deviation 1. So if we are looking at probabilities of the normal distribution of capital X between A and B, it is the same thing as you are subtracting minus mu. So basically what it says here is, so if I subtract mu from here, so what it will be, X minus mu, that means you're going to do it through the whole A minus mu less than equal to B minus mu, and then you divide by sigma. So when you divide by sigma, you divide by sigma, you divide by sigma. And here is, outside is the probability. So this X minus mu sigma is nothing but C. And remember, what is the meaning of probabilities? That is the area under the curve. So it doesn't matter if you're talking of a normal distribution with means which is not normally 0 and 1. The area under the curve, what is the value we're going to get, is exactly the same as we are applying this transformation of Z, which is X minus mu over sigma. The areas are normally the same. Here we are going to have a normal curve. On the other hand, when you take this transformation, now we will be under the standard normal curve. So if this is mu, remember in the standard normal curve, mu is 0. If this is A, then in the standard normal curve, it will be A minus mu over sigma. Similarly, if the right end or the upper values for the X is B, which is equivalent to B minus mu over sigma. This is just to give you a view of it. What we'll be basically using are our calculators to do the work. Now let's talk about Z-scores. Remember when we were doing chapter 2, descriptive statistics, we talked about Z-scores. So Z-scores are nothing but x minus mu over sigma. So if you have a normally distributed random variable, say capital X, then the Z-score is basically x minus mu over sigma. And this is basically, we are standardizing the normal distribution of X. So when we say the standard normal distribution, it is nothing but the normal distribution of standardized values called Z-scores. A Z-score is measured in units of the standard deviation, and a Z-score tells how many standard deviations the value X is above, which is basically the right of the mean mu, or below to the left of the mean mu. Let's look at some examples. For example, if I say capital X has a normal distributed random variable with mean 5 and standard deviation 2. So I would like to find the Z-score when X is 11. Okay. Now remember the formula for the Z-score. Z-score is X minus mu over sigma, which is basically your X is, now remember this is one of the values your normal random variable is taking. So we'd like to know what is the Z value which corresponds to 11. So we write 11 minus 5 by 2, which is 3. Now keep in mind when I say X is a normal distribution 5 and 2. So if you remember this, let me see if I can make it nicer here, looking here, to show you what basically this means in terms of the normal distribution. So I'm just going to make a small little bell shape for the X and a standard normal curve here. So this, guys, is my X. So this is the X normal curve. The amount is 5 and we are going to standard deviations either side of the mean. It's 7, it's 8, and it's 9. Okay, now let's go back on the other side. So it's going to be, you're going 2 standard deviations. It's going to be 3, it's going to be 2, 3, and then it's going to be, 1, and then it's going to be negative 1. Okay, now remember when we use this Z-score, what's going on? This Z-score is going to be equivalent to, 5 is going to be equivalent to 0. Oh, I'm sorry. What am I doing, guys? I did something wrong. Totally wrong. Here, sorry. We're going 2 standard deviations, not 1 standard deviations, guys. I'm sorry, I'm wrong. So 7, 9, 11. Sorry, guys, I was wrong. Thankfully, I got it. Okay, so here's it. So 5 is, remember, when I put 5, this is the mean for the normal curve. But for the standard normal curve, 5 is 0. When it is 7, that means we are going 1 standard deviation. This is 1 standard deviation to 5. That's 1. 2 standard deviations to 5 is 9, whereas the standard normal curve will be 2. And when you have 3 standard deviations to 5, you will get 3. This, guys, is the standard normal curve, or normal distribution, you could say that. Okay, so when we are saying what is 11, look at this one. Here my 11, guys, is 3 standard deviations above the mean 5. Do you see it over here? Now, if we actually have seen it also by doing it by hand, but if we don't want to do this by hand, we can just apply the Z-score, and this Z-score automatically says how many standard deviations we are above the mean or below the mean. So this one basically says it is 3 standard deviations above the mean. Let's look at an example. Okay. The example is, some doctors believe that a person can lose 5 pounds on an average. Okay, so on an average, you're losing 5 pounds. That means that's the mean, guys. In a month, by reducing his or her fat intake and by exercising consistently. Suppose weight loss has a normal distribution. Okay, we are assuming this little weight loss is the random variable here for us, has a normal distribution. And this random variable is the amount of weight lost in pounds by a person in a month. We are going to assume, because it's a normal distribution, we can write this as x has a normal distribution of 5. This is the average which is coming from here, because it says doctors are believing a person can lose 5 pounds on an average. So this is where the mean goes. And the sentence just before that, it says uses a standard deviation of 2 pounds. That means that's my sigma. Okay, so if x has a normal distribution with mean 5 and 2, what is the z-score when x is 10? So when x is 10, what is the z-score formula? Z is what? X minus mu over sigma. What's my x, guys? 10. My mu, 5. Sigma, 2. What do we get? 5 over 2, which is 2.5. So what is the z-score which corresponds to 10? It's simply 2.5. Now how do we write it down? So what is the z-score saying? The z-score says that 10 is 2.5 standard deviations to, remember, it is positive. It is to the right of the mean, okay? Right or above the mean. Keep that in mind. Okay, because n is 5. 5 corresponds to 0 in the z distribution. Continuing with the same example. Some doctors believe that a person can lose 5 pounds on the average in a month. I'm just repeating this problem again. By reducing his or her fat intake and by exercising consistently. Suppose weight loss has a normal distribution, and we are assuming the random variable is the amount of weight lost in pounds by a person in a month. So losing weight is in a positive sense we're looking at here. And we're using a standard deviation of 2 pounds. That means x is a normal distribution. Now here, suppose a person is gaining weight. So gaining weight means we are going on the negative. So here that means we're talking of a negative weight loss. Remember, weight loss is basically in a positive sense, but when you say if you gain 3 pounds, that means you're having a negative weight loss. That's what it amounts to. That means x is minus 3. So how would my z-score look like? So z would be x minus mu over sigma. X is minus 3 minus 5 over sigma is what? 2 minus 8 over 2 minus 4. So basically, the z-score is minus 4. Remember, this minus 4 is meaning that the z-score, if a person has gained 3 pounds, that means the z equivalent is gaining 4 pounds. Now, what does it mean? The z-score says that x equal to minus 3 is 4 standard deviations. Standard deviation here is to the left. The negative is basically left. Keep in mind. So we do not write negative 4. We just simply say it's 4 standard deviations to the left of the mean. Okay. Let's look at another example. The final exam scores in a statistics class is normally distributed with a mean of 63 and a standard deviation of 5. Let x be the normal random variable which represents the exam scores of a statistics class. So we're talking of a normal distribution. Remember, when you see these words normal, wherever you see normal, oh, I am having a normal distribution. So what is the notation form? Remember, the notation form is n, and we need the mean. Mean is 63. Write down 63. And standard deviation, 5. Now remember, whenever we write this one, mostly what we do, we create a little normal curve, a little bell-shaped curve, write in the terms. So we have 63 and a 5 is what? 68 and a 5, 73 and a 5, 78. So always write these down because they help us a lot. Let's go backward. So 63 minus 5 is 58, minus 5 is 53, and 53 minus 5 is 48. Okay. Okay, hopefully my numbers are right, guys. Just want to recheck it. Okay. Well, the number seems to be right. Good. Now let's go ahead and look at the first problem. Find the probability that a randomly selected student scored more than 65. Okay, so that means probability x is strictly greater than 65. This is equal to x strictly greater than, remember that is normal CDF, the formula we have been always using. Greater than 65, that means this is the lower bound, 65 lower bound, lower value, anything what you think of. Remember the positive is 999, and then we have the mean is 63 and 5. Once again, what are we going to do, guys? We are going to go ahead, get our calculators, get your calculators, guys, and put these numbers and see what we get. Okay, so second inverse, and then we go to the number 2, enter. Now remember, the lower value was what? 65. Upper value, simply write 999. What was the mean? The mean was 63, and the sigma, the standard deviation is 5. Cursor to the paste, enter, enter. We get what? 0.3445. Okay? So it's 0.3445. Let's write it down, guys. Our answer is 0.3445. Continuing with the same example. Here the question is, it's the same example, x has a normal distribution with mean 63 and standard deviation 5. Here the numbers are, guys. So find the probability that a randomly selected student scored less than 85. So probability x is less than 85. Okay, this is going to be what? Once again, normal CDF. It's less than. That means this is the lower bound. 85, it's less than 85. Yeah, that's the upper bound. Sorry, guys. Okay, so that means what are we going to do? We are going to be writing that little negative 999. Keep that in mind. 85, 63, and 5. So let's go ahead, take our calculators. So it's normal CDF, second inverse, number 2, guys. Now remember, that's maximum, it's less than 85. So that means negative. So this is the negative, guys, where my cursor is, right at the very bottom with the little, negative symbol with 2 parentheses next to it. That's the one we're going to write. And we better take the cursor onto the, here, negative 999. And we are having 85. The mean and the standard deviation will remain the same. Just take your cursor, click, 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 guys. Okay, so then we have paste and click. What's the answer? Almost 99%. Okay, so let's go write it down. 0.4 times 9. 0.9999. Okay, let's look at the question from a different perspective, because we were always finding probabilities. Suppose we are given the probability and we would like to find what is the value which corresponds to that probability. Okay, so that's a question here. So it says the final exam scores in a statistics class is normally distributed with the mean of 63 in standard deviation, and x has a normal variable which represents the exam scores. The question is find the 90th percentile. What simply it means is find the score K which has 90% of the scores below K and 10% of the scores above K. Okay, so when you see the question is find the 90th percentile. In other words, you're given the probability and you're asked to find the value on this little x, the horizontal line that corresponds to that 90% of observations below it. Now to do this problem, guys, you have to use the statistical function inf_norm. So we're going to do that. So inf_norm, so let's go ahead, get our calculators. Pick up your calculators, guys. And once again, do second and vars. Now this time we go to the number 3. Take the cursor to number 3 and then you press enter. Now here is the area. Area which we always put over here, guys, is 1 to the left of what we are looking at. And we're given the 90th percentile, so it's 0.9. That's what it means. Now by default, remember it's 0 and 1, but we are given that the mean is 63 and the percentile is, the sigma, standard deviation is 1 and the tail is to the left. Just keep it to the left, don't do anything else. And then paste and then press enter, enter. What's the number we are getting? 69.4. Okay, this is the number 69.4. This is the latest calculator, guys, so you're going to see this one. The old calculators will have only 0.9, 63 and 5. So do not worry if you do not have the left, okay? But you will still get the same answer. So 69.40. And that's what we have, 69.4. Now, a similar kind of example, guys, we'll start with. This is a wingspan of recently cloned monarch butterflies. And we're looking at this monarch butterflies. These are the wingspans. They follow a normal distribution with a mean of 9 inches and a standard deviation of 0.5. Now, we'd like to know what proportion of the butterflies has a wingspan less than 8, wider than 10, and more. But before we do all this, let's write down what we have been learning. So because these are the wingspans, that's what's your random variable, the length of those wingspans we are talking about. It has a normal distribution. Remember, whenever you see the word normal, look for the word mean, look for the word standard deviation. Okay? Now, so X has a normal distribution, guys. Mean is what? 9. Standard deviation, 0.75. And remember what I always tell you? Please go ahead, make that little bell-shaped curve. Oh, this came out good. Okay, let's write on the numbers. 9, 9.75, then 10.5, and then we have what? 11, do we get what? 11 or 12? What do you think? Oh, 11, guys. So we have 11.25. Now let's go on the other side. So we subtract from 9.75, we get 8.25. Another subtraction is 7.5. Okay, 7.5, and the last one is going to be 6.75. Okay. Okay, guys, my pen is acting a little funny with me. That's okay, we'll handle it. 6.75. Wow, that came out good, right? So let's look at the question. It says, what proportion of butterflies has a wingspan less than 8 inches? That means probability X less than 8. Now, you should be a pro by now, guys. I hope so. So I'm just going to write down the formula, normal CDF. Less than 8 means you're going to have negative 999, then 8. Remember the mean is 9 and 0.75. Okay, go ahead, get your calculators, guys. Practice time. You can be faster than me. Okay. Okay. So let's do second and vars, and we take to the number 2, press enter. Now it's less than 8, so it's already doing the work for us. We don't have to worry. Lowers is done. Upper is what? 8. Then mean is 9. and the standard deviation is 0.75. Okay, so what do we get? Take the cursor to paste, enter. It's 0.09, 121. Okay, let's write it down. 0.09, 121. 0.09, 121. Now here it says, with the wingspans are more than 10 inches, that means probability x is greater than 10. Greater, that means this one is the minimum value, okay? Or it is the lower value, whatever you guys are comfortable calling. So normal CDF, it's going to be 10, and then write 999. 9 is the mean, 0.75, and when you plug it in, I'm just going to write down the answers for you guys over here. It's going to be, again, 0.09, 121. Okay, let's continue further. Now, again, it's the same problem, but here the question is, what is the proportion of the butterflies that have a wingspan between 8 to 10 inches? So that means we're looking at probability 8 less than x less than 10. What's the formula, you guys? We're going to do normal CDF. 8, 10, 9 is the mean. Remember, that's the mean we're talking about, standard deviation, 0.75. Once again, when you plug it in the calculators, I know now you're much more calculator savvy now. So the answer is 0.81757. Okay, now let's look at this next problem. This is very similar to we just talked about, those finding the points on the horizontal line. Okay, let's read the problem. It says 10% of butterflies have a wingspan wider than how many inches? Okay, guys, let's first draw the bell-shaped curve for us, okay? So here's my bell-shaped curve. And the percentage, that means I'm given the probabilities, keep in mind, okay? So I have my 9. It says 10% of butterflies have a wingspan wider than how many inches? Remember the horizontal, guys. This horizontal line represents the, the wingspan length. That's what it basically, it's the length of the wings of the butterfly. It's a wingspan. That means these are the values. This wingspan is in inches. So we say, oh, it is x. Okay, so it is this x. Suppose it is x. Now if it is, I said x and I'm writing k. Okay. So let's say, okay, suppose this wingspan, which is how many inches? We say, let it be k inches, okay? So this is, guys, k. Now it says 10% have a wingspan wider than these inches. That means 10% is this. Wider means it's more than k, okay? So that means we are basically looking at this. This is given to us. This, guys, is 10%. Now, most of you will have calculators which are basically going to look at the left-hand side. So that means how much is on the left-hand side of this value k? That, guys, is 90%. So we like to find this k. So if you remember the formulas, k is INV no. And most of us will be having a calculator which is like a little old than the one I have here. So when you will be writing it down, you'll be writing 90%, guys. So it's going to be 0.9. Then you write down the mean and the standard deviation. That's 9 and 0.75. And what you get the answer. So let's go ahead and get our calculators. So it's going to be second and was. And remember, not this time because we're looking at the value on the horizontal line. So we're going to look at number 3, inv no, okay? And when we do press enter, this line which you're looking at tail will, most of you guys won't see it. So Because of that, I'm just going to focus more on the area, and this I'm going to just leave it to the left. So area is 0.9. Mean, guys, remember, was our 9. And the standard deviation is 0.75. By default, it is left. Let it be left, guys. For people who, students who have, or who are watching this video, you will be, if you do not see tail, that's okay. You definitely will have these 3 on your calculator. Then take your cursor to paste and then press enter and enter. You will get 9.96. Now remember, this is a word problem, it's inches. That means 90% of the butterflies have a wingspan less than 9.9611 inches. Okay, let's write it down, guys. So what's the answer? This is 9.96 inches. Thank you, guys. And then we will continue talking about later of normal approximations to binomial distributions.